Good afternoon. So first off, I'd like to say that I do have a book, this wonderful O'Reilly book, Systems Thinking for Software Engineering, Making Sense of the Madness. And maybe one day I will actually write this. But first off, why did I choose a crab for the cover? How many times have crabs independently evolved? Like a bunch of times, at least 5. They're not sure. They keep finding new, completely unrelated species of crabs that have independently evolved. So the ocean is a system. And that system wants to make crabs. It does. It really wants to make crabs. And the same is true of trees, actually. Like, trees are sort of unrelated. So what does this tell us? It tells us that systems shape outcomes. And systems are important. I mean, we're all systems thinkers. Every talk that I've seen in this track so far has basically been about people saying, hey, so I made this intervention and here is how it affected the whole system that I work in. So you're all systems thinkers already, and all I'm doing is I'm giving you, a few ways to structure the way that you're thinking about your systems. So what is a system, briefly? You've got multiple elements or parts, and they have interactions and interconnections. And if you're engineering a system, it's got a function. And those are the 3 sort of parts of your system recipe. Obviously, not all systems are engineered. Systems thinking has this like weird and wacky kind of lineage coming from, cybernetics back in the early days of sort of computing and operations research, but also from biology and all sorts of other places. So a tree is a system, and your engineering organization is a system. You're a system, and the technical systems that you work on are systems. And the whole internet's a system. Systems everywhere. Where do you stop? You stop at the function level that you care about. So, complex systems are a special type of system. They have nonlinear interactions and feedback loops, which means that a small change over here, the butterfly flapping its wings, can make a big change somewhere else. Complex systems, they have parts of the systems have memory and state. And that means if you do the same inputs today, because the state of the system is different, you might get radically different results. They're also very hard to understand and predict behavior for that same reason. So when we build distributed computer systems, I think as most of us in this room, they are complex systems. They're dynamic. Your system is always changing, always operating. It never stands still. Requests are flowing through it. It's, doing batch jobs. It's, you're doing migrations. You're doing all these things. There's always a little bit of chaos and unpredictability. So running these systems is hard, especially because of the way they change. They're never the same as they were yesterday. So we can do 2 things. A lot of the efforts to make your computer systems more reliable actually turn out to be about making them less complex. I think a great example of that is, has anyone read the Constant Work and a Great Cup of Coffee by Colin McCarthy? It's in the Amazon Web Services System Architects Library. It's well worth a read. But that paper basically says, hey, instead of doing things that change according to how many of your system's participants are health checking up or down, we're just going to push a big table every 30 seconds, no matter what's going on. That makes it more reliable because there's less complexity in the system. But there's a lot of other things that we can do as well. So interactions. Interactions are probably a pain point for nearly everyone, I would think. Who here has ever seen a bug that happened because of the way 2 systems were interacting? Yeah, all of you. Like sometimes system A and system B, they're both working the way they're supposed to work, but oh no, you have a problem because of the different expectations or some sort of an unexpected interaction. And this great paper here came out in this year's Eurosys 2023. I'll put the link here. Well worth a read. It's exactly about all this. So if you want to tackle these kinds of interaction problems and these sorts of challenges in running our complex technical systems, systems thinking is quite helpful. So what we're talking about here are tools for working with this complexity. And like I said before, this is all of what we're doing at StaffPlus level. Like this is our bread and butter. So we're going to move through a few systems thinking tools. The first one is called the energy barriers perspective. And this one is not often thought about as a systems thinking tool. So I sort of threw this in here from my safety science studies that I'm doing at the moment. So this comes from physical systems like people who are running train networks and road networks. And the idea here is you want to prevent uncontrolled transfers of energy. So in a road network, you might prevent it by avoiding driving vehicles, probably not practical. Reduce the amount of energy, so smaller vehicles, lower speed limits, traffic calming measures in the road network. We can install ABS to control the release of energy, make it direct it the way we want it to go. We can modify how the energy is distributed with seatbelts, crumple zones, and we can separate potential victims from the energy. So put pedestrians on footpaths and not on the side of the road, that sort of thing. And then finally, we can do damage limitation, which is first aid and emergency medicine and rehabilitation. So how can we apply this kind of perspective to software? I'm going to use an example here, which is the one time that Google deleted its entire CDN. This happened in around 2016, I think. The intention was to decommission one rack of machines. There was a command line tool, which basically didn't understand the input it was given. So it said, well, if I don't understand the input I'm given, I will delete the world. Of course. It's surprisingly easy to build in these kinds of bugs or assumptions, right? So deletion was basically also instant. So it wasn't physically overwriting sectors on disks. It was instead throwing away encryption keys, which you can do super fast. So applying the energy barrier perspective to our CDN deletion incident, we have prevention, which is don't decommission machines ever. Well, we can't do that. We need to do this as part of our workflows. But we could rate limit how many CDN machines we would decommission over an hour or a day. We could give better feedback in the tooling. We could modify the process to have an undo. We could zone our infrastructure so that you need different permissions to do work in each part of your infrastructure. And we can we can mitigate by building automation to rebuild them faster. So what I like about this perspective is it makes us think not only about, okay, the CLI tool was bad, we should fix that. It makes you think about all the different parts of this workflow that are interacting and what you can do at each stage of the whole operation to make it work better. Now, obviously, you're not going to do all of these things. We live in the real world. Some of these are expensive, but what you're going to do is you're going to use this to sort of give you a menu of options. And you're going to say, okay, well, the trade-off is probably to do these 2 or 3 things, and we'll move on from there. So the next technique I want to talk about is called causal loop analysis. And so this comes from MIT's Sloan School of Management back in the 1950s. Peter Senge wrote about it in the 5th discipline, which is kind of about management. You can model basically anything in a causal loop diagram. It's really for modeling these kinds of feedback loops and these kinds of interactions. This one here is from this book here, Limits to Growth, where somebody at Denali Meadows, in fact, is modeling basically the dynamics of food supplies in industrial society. So, it's pretty broad. You can actually use this for your socio-technical sides of your systems as well as your technical stuff. But it actually works super well for a lot of distributed systems problems. And here is an example. So my little 6-line of code distributed file system. So we have blocks of data, and we want to make sure that we have enough replicas of each block. So we are going to periodically iterate through all the blocks that we have, see if all the replicas are heartbeating okay, and we have enough replicas, and if not, we'll copy some new replicas. Straightforward. Here is a little diagram of what would happen if we lost a node. So we have this pink block and this blue block. And we have 3 copies of each one, and we want to have 3 replicas of each bit of data. We lose this node here with the lightning strike, and we end up doing this copy to retain this invariant of 3 blocks of data. So far, so good. Okay, we'll start our causal loop analysis. So the more replication we have of chunks, the more system load we're going to have, because it's not free to copy data around. That takes network, it takes disk reads. If system load increases too much, we might get some failed heartbeats, which might lead to some more replication, okay? So we can see already that we have the start of a feedback loop. We have these plus signs that we add here to show that basically if we have more of one thing, it feeds into more of the next thing. You can also have minus loops as well, which means if this goes up, that goes down. So this cycle lives in an environment. So we have write load coming from users, we have read load coming from users, we have potentially hardware and power failure, and these affect our sort of central potential feedback loop. If we add more replicas per block, after some time, we might actually see a reduction in average system load because each instance may be doing less work because there's more copies of the data around the place. Now, most of the time, you're going to go around this loop and everything is fine because you're not going to tip over the point where your system load is going to start causing a bunch of failed heartbeats. And this is your sort of your happy, steady production state. But sometimes, maybe you will lose a whole rack of machines. Or maybe you'll have a wacky bug involving a leap time second, and I can tell you that story afterwards. And what will happen now is your system will try and replicate everything, and your stuff might go on fire, like figurative fire. So this reinforcing loop here always has the potential to become a sort of a runaway vicious cycle. And that's something that we can see very clearly when we start building these kinds of diagrams. We can see what tends to reinforce and what tends to balance out. And what we do about that, of course, is an architecture issue. Typically, we can do things like we can add delays to make it less likely we'll tip over that edge as a result of some coordinated event, like a big rack failure or a data center failure. Or we can do things like we can add some sort of rate limiting, which is sort of like putting a little balanced loop inside of your reinforcing loop to prevent that runaway. So there's things that we can do. And I find that this kind of analysis is very good about thinking, what are the influences in the systems we build? If I change this over here, how might it change all this other stuff over here? So it's good. This is a good way of thinking not only about reliability, like in this example, but it's also quite good about thinking about efficiency. I mean, what causes costs in our systems? Where are bottlenecks? And how can we kind of spread things around? This is a great kind of way to think about inputs into any sort of disaster testing scenarios that you have, whether it be tabletop exercises or something practical. You know, think about what of these parameters, what if these inputs change drastically? What if I suddenly have a lot of write load? What if I suddenly have a lot of failures? You can kind of see the things that you can tweak to create these kinds of disaster testing. Now, when I told one of the lecturers on my safety science course that I was going to talk about hierarchical task analysis, he was like, no, why would you talk about that? Because he sees this as this dreadful sort of Taylorist thing where it's used for human processes. I was like, oh, well, the human being does this and this and this, and it is probably pretty bad when we try and break down human work into goals, sub-goals, operations, and plans. However, it is very good for computers, because computers actually are very happy all day doing the same thing again and again in the same way. So let's say we are still working with our distributed file system. We would like to be able to serve user requests and store files and some other stuff. So in order to serve user requests, we would like to make sure that we have sufficient disk space to store the files that we have. So in order to do that, we can do a bunch of sub-goals, and this is, I guess, stuff we're doing at the sort of the team level and the system level. The lines are a little bit blurred here. So we would probably do long-term capacity planning. We would look at how much disk space we're using now, and we would make, and you know, how is that curve changing, and you know, how many machines should we buy for next quarter? We can clean up deleted files. We'll need some processes for that. We should alert if our disk space used becomes too high, of course, just in case, just our backup. But we should reject writes if the system disks are full. You know, if we don't have any space, we can't accept your file. We can't tell you that we can accept it. So what does that look like? It looks like this. First, we need the set of machines that are part of the system. So we'll read a service catalog or some configuration or something, right? Now, step 2, which is the second column here on the left, we're going to add up the sum of the reserved disk space for the distributed file system. So each machine in the system presumably knows how much of its disk is dedicated to the distributed file system. So it'll have some configuration or something that will tell it that. So we're going to have to go and we're going to ask all of these machines to tell us how much, and we'll add it up. So probably this happens in a monitoring system, I would think. But we're focusing on sort of the task rather than the architecture here. So then the next thing is we need to add up how much is actually stored in this system already. So we take the sum of the disk space used by the distributed system. So we do that by, for every machine, again, ask it to add up the space used by all its files, or do a disk usage command or something like that. Now, the fourth thing that we do, compute available space by subtracting the result from 3 from the result from 2. Straightforward, yes? Excellent. Now, here's where we can do something interesting with it. This can become the input to a thing called EastBL, which is Event Analysis of Systemic Teamwork Broken Links. And I had to put that on the slide because I could never remember it. So you start off with one of your hierarchical task analyses that we just did, and then we ask, what would happen if each link was broken? We don't have to think about how it gets broken, because I think you all know in a distributed system, it will find a way. Somebody will break an API, or the response will be too big, or some random thing will happen. It's not even about network connectivity. What would happen if there was some catastrophic bug that meant it gave you just a ridiculous answer? So let's say something goes wrong with 3.1 and with machines figuring out what their disk space used is. That's going to affect the summing, and that's potentially, if it's wrong enough, that will make your system reject all the writes. And in fact, we saw this happen once, and I know people hate the @Google stories, but at Google, one time there was a bit flip that made one of the distributed file system machines report that it was using several exabytes of disk storage, which was way more than disk that machine had available, and it meant it looked like the entire cluster was out of disk. Now, that's silly, but it happened, right? So, and there are many other sorts of ways that this sort of thing can happen, like software bugs, they happen. So what do we do about that? I mean, that's going to be context dependent, system dependent. In this context, maybe you can add some guardrails around, what sort of numbers you might believe from each machine. Maybe you would have some accounting that does some sort of asynchronous verification by a different method, that sort of thing. But maybe you would have a delay on if you suddenly see it jump up by several exabytes, you might be suspicious before you start rejecting all your writes. So there's a bunch of things you can do to make that system more resilient. But the point of EastBL is not to figure out what to do exactly, but to look at your system and look at the ways that things can go wrong in it. So you can do this sort of stuff for anything. We tend to build very, very basic, blocky architecture diagrams when we describe our systems. But do you ever build diagrams that show how your rollouts work? Your configuration update mechanisms, your credentials, how your autoscaling works, how do you do traffic shifting, how does your resharding and your backups, all this kind of stuff, all of your control and management plane actions. All of this stuff is super important, and it creates quite a lot of outages and reliability problems, and it's a huge amount of the complexity of the systems that we build, particularly if you're on the operations side. And we don't think about them when we don't talk about them. They're just sort of these invisible things. Like we just think about the data plane and we don't think about the rest. So HTA and EastBL are really good ways to think about how how those planes are working and how you can disaster test them, how you can think about them. Now, I've run very quickly in 20 minutes through 3 tools that you could probably talk about for hours, if not days. And there are many, many more systems thinking perspectives than these. So STAMP is a big one. That's from MIT, Nancy Levison. It's thinking about reliability in systems in terms of controls and hazards and constraints that you can use to prevent your system getting into hazards. Then there's another one called the functional resonance something something, FRAM, which is also very good, which again is talking about, it's another one that's really good for looking at the control and management of your systems, because it talks about how all the different pieces of work are interrelated, what the prerequisites and inputs and outputs and control actions of each of them are, and how they use resources. Those are excellent as well. There's really good information on the internet available about all of these. But you're not going to use everything all the time, so you should use what makes sense in your situation. Systems thinking tools can provide excellent documentation. Text is great. I love text. But it's often very good to back up your text with some graphical stuff. And all of these systems thinking methods, apart from energy barrier, tend to, they give you nice diagrams that you can put in your documentation that will be memorable. Hierarchical task analysis, for example, is very good for debugging. Like if you were looking at a system and you're stumped as to why it is doing that thing, hierarchical task analysis is a great place to start, because it gives you like boxes that you can look at saying, could this thing be happening as a result of this thing going wrong? And like I said, you can use these methods for thinking about human scale problems as well, not just the computers, particularly the causal loop diagrams. I mean, think about the whole DevOps sort of feedback loop of you make your deploys safer and easier, you get people to do them frequently, you get fast feedback, and your velocity increases. That's a feedback loop, in a human system. Here are some books that I like. The one in the middle, the Handbook of Systems Thinking Methods, is geared towards engineers, not software engineers specifically, but engineers. Thinking of Systems is more general, and Engineering a Safer World is by Nancy Levison, who is an amazing safety science and systems person and a researcher. And the Open University, since we're in the UK, also has a free course, which is pretty good. They talk more about the human side, how to do organizational change. And systems thinking, the real takeaway, ask better questions. It helps us to think about the questions that we should ask. And that is one of the hardest things that I think we do as staff engineers. So here is, you can find me. I think these slides are going to be published. I'm happy to answer email. If anyone would like to know more about load management and isolation, we have a link here. And I will get off the stage because my time is up. Thank you so much.